And so next up, we have Tadge Dryja, who will be speaking about discrete log contracts.
Cool. So yes, I will start talking about discrete log contracts. They are a form of privacy-preserving smart contracts on Bitcoin. And this is for today. So intro, hi, I'm Tadge Dryja, work on Bitcoin research here at the Digital Currency Initiative, co-authored the Lightning Network paper, and there's a lot of similarities with this construction I'll talk about with discrete log contracts. So recap for Lightning Network, authored this several years ago now, and it seems to be people are using it, people are developing on it, which is cool. There's several companies looking at this technology, different variants on other blockchains. And the general idea is these network of payment channels. And a payment channel has a couple properties. The idea is you're creating some type of output or some type of account, whatever it is on your network, and that's sort of globally broadcast. And then once you've created that, you can update it a lot of times. So you don't tell the network about every state change. You only tell the network about sort of the incoming, the initial setup state and the final outcome. And in Lightning Network, the channels revoke old states. So that's one of the tricky parts of it is how do we sort of tear up the information about what our previous state, what our previous balances were. And you can't prove that you've, deleted a private key, or you can't prove that you've deleted something to someone else, at least not with regular hardware and regular assumptions. But the construction in Lightning is sort of giving someone a key, and having your own keys be time-locked in some way is effectively tearing up your claim to something. Because you're saying, okay, here's here's total control of something if I ever broadcast it. So that shows that I won't broadcast it. And we can use this to make sort of a general class of conditional payments. So smart contracts in general, what you really want to be doing is paying based on some kind of external data. Another way to talk about conditional payments is bets. So I sort of think in computer science terms, everything's a bet, right? Buying things, selling things. Insurance is just bets. So if I get car insurance, I bet I'm going to crash my car, and the insurance company says, I bet you won't. And then if I crash my car, I say, ha, I win, you got to pay me. And if I get health insurance, I'm betting, Blue Cross Blue Shield, I'm not going to get cancer. And then they say, oh, wait, no. I say, I bet I'm going to get cancer, and then they say they bet I won't, and then if I get cancer, I laugh and say I win, but no, it's not funny. So we want conditional payments. They're like all of finance, right, is conditional payments. And in Bitcoin, we have conditional payments, right? There's opcodes, and then the whole thing is to verify whether this payment is valid or not. But they're very constrained in what incoming data there is. Right, so we've got opcheck.sig. We can check cryptographic signatures, and we can check, time locks and things like that. And we can add two numbers together, but that's not useful. We don't have, op weather, so we can't query the weather as an opcode. So you can do a lot of really cool stuff with signature verification and the time locks. Very powerful right there. And we're getting more new cool stuff in Bitcoin, like Schnorr Taproot. But there's no clear mechanism for external data. And the reason op weather is sort of a joke is, well, whose weather, where, and how can you verify this? The idea in Lightning Network, I would argue Lightning Network uses smart contracts. It's a fairly simple script. But it is enforcing a smart contract. But there's no external data. Or if there is external data, that data is created just concerning the channel itself. Right, so it's just Alice and Bob have this channel, they're doing some things, and they're using data created by this interaction and then enforcing smart contracts on chain. But if we want some external state, we need to get some kind of oracle, right? Some kind of method, and I'm using oracle in a very general sense here, some method to get data about the real world into this cryptographic system. And so the simplest oracle you can really use is multi-signature. And you can't just do 2 of 2. So if you want to make a conditional payment, let's say Alice pays Bob if it's rainy, Bob pays Alice if it's sunny. A 2 of 2 multi-sig, which has been proposed and can probably work some of the time, means that any kind of conflict freezes the funds. So if it's basically a handshake bet where it says, okay, I'll pay you if it rains, you pay me if it's sunny, and then they disagree, right? And then you get into all sorts of game theory where rich players may be at an advantage because they have a lower time value of money, so they're, I'll wait out the clock. It works great with friends, but Bitcoin is the currency of enemies. And so you could suggest maybe a third party, an adjudicator, to decide in case of conflict. So like a 2 of 3 multi-signature oracle. And this can work, right? There's, generally insurance is another form of bets, and there's some kind of 2 of 3 third-party oracle. They call it, a claims adjuster or whatever. Someone to come, wait, did you actually crash your car? And they come and they look and they're like, yeah, that car's crashed. Or they ask the police maybe, did they crash his car? And you want you want there to be an Olivia, in this case, oracle, to sort of adjudicate between Alice and Bob disagreeing about whether Alice has cancer, whether Alice crashed her car, or whether it's raining. So if they do disagree, if the thing is though, this is an inherently optimistic protocol, right? If Alice and Bob agree that yes, your car crashed, I'm not going to bother looking into it, or yeah, it's obviously raining, then they can resolve this without contacting the third-party adjudicator. But if they fight and they disagree or they're unresponsive, then someone can ask Olivia to sign. The problem is that this can lead to like bribery, right? So it's sunny, and Alice tells the oracle, hey, this is Alice, I just lost a bet, but say it's raining, and I'll give you 0.8 Bitcoin, right? We bet 1 Bitcoin, and I lost, so I'm going to lose everything. I've got nothing, nothing at stake at this point, and I can try to bribe the oracle. So the idea, the motivation behind this is that oracle interaction is dangerous. There's a lot of people want to and are using oracles to sort of put data on chain. But the fact that the oracle sort of knows who's using the data or why they're using it or what they're doing with it, the oracle is the link to the real world, but you kind of want to put them in a box and say, no, you just send some information about the real world, and that's it. We don't want you to be able to be influenced. So in a 2 of 3 multi-sig oracle setup, they get to see all the things they're adjudicating, right? So if someone's coming to inspect that someone's house burned down or someone's car crashed, they see that the house burned down, right? This is obvious. And they also they know they're deciding the outcome of every contract that's based on this data. And they can equivocate, right? They can say that in this case that, this car crashed, and someone else that there wasn't a 6-car pileup and conflict that way. So it'd be better if the oracle couldn't equivocate, and even better if they never saw the contracts that they were, influencing. But how do we do this? Okay, so going to some math. Schnorr signatures, which, at least to me, I'm very familiar with these equations at this point, but this is because, this is what I work on. But it's a signature scheme that is not yet used in Bitcoin, hopefully will be soon, was patented for a long time, so didn't really get widespread adoption, but the patent has expired, and so people are now doing much more implementation and research on this. Yeah, a little time. So the basic idea is you're creating this random, you have your public key, A, you have your private key, little a, you multiply by a generator point to get your public key. So you start out with a random private key, do some multiplication to get your public key, and the idea, the hope, is that no one can invert this to find your private key from your public key. To create a signature, you create essentially a new private key, we call it K, and then essentially a new public key, the sort of one-time use private key and public key that you're going to use specifically for a single signature. And then to sign, you're basically taking your one-time use private key, subtracting, or actually adding also works, subtracting the hash of your message and that public one-time use key times your private key. This is verifiable by any party that has only public information. So to verify this equation, you just basically multiply both sides. There was a laser. Ooh, there's a laser pointer. You verify both sides of this s equals k minus hash times a. You multiply both sides by g, so you get s times g equals k times g minus this hash times a times g. And k times g is just r, a times g is just big A, and this hash is all public information because it's the message in R, so it's publicly known. So once you've got S, to verify, you just multiply it by G and see if it equals that. So discrete log contracts uses a sort of modified Schnorr signature. And one thing that's I've seen a lot of sort of confusion about is that it doesn't need to do this, the construction I'm about to talk about, you don't need to be able to enforce Schnorr signatures on Bitcoin. The end result of this is a key pair, this sort of little a and big A, that can be used for regular elliptic curve digital signature algorithm, or Schnorr signature, or whatever you want to do with it. But we're using Schnorr signatures only offline. Wait, yeah, already had that. So I guess sort of this is introducing or using what I'm calling a fixed R pub key. So you're pre-committing to that one-time use key. So normally we think of your pub key as A, and then your signature is the tuple R comma S. But in this, to say, like, well, let's think of the pub key as A and R, and the signature is just S. It's the same equation. It's the same things. We're just sort of reconsidering what components we think of as a public key and what components we think of as a signature. Normally, so this is totally fine. The equation works. The reason nobody does this is because you can only use this pub key once now, right? So quick, I'm not going to go through it, but if you use the same K value for two different messages, anyone can now sort of subtract these two signatures and divide, essentially, multiply by the multiplicative inverse of other public information and find your private key. Fun fact, this broke PlayStation 3 signing code back in the day because whoever was implementing this said, okay, K needs to be this random value. They picked a random value and just used it every single time they signed. But it needs to be a different random value each time. So this is not generally a breakthrough in how signatures work. This is an obviously worse signature, but it has some nice properties. Given a pub key, which we're now defining as A and R, and any given message M, you can't compute S, right? If you don't know the private information, that would be forging a signature. However, you can compute S times G, which is just R, which you now know because it's part of the pub key, minus the hash of the message in R times the pub key. So S times G is computable for any given message M if you know this sort of new, expanded, modified one-time pub key. This is useful because now we can think of that signature S, or rather S times G as a public key and S as a private key, right? They're equivalent, mathematical things, like S is this scalar and S times G is going to be a point on the curve. Normally, we multiply S times G just to verify a signature, and then we throw it away. But in this case, we're saying, well, let's think of it as a public key and use it as such. So we use that because the third-party oracle is now going to sign messages and reveal a private key. So the idea is that when the oracle initially publishes a public key and a one-time public key, so this A and R, and then the users anticipate messages that it could sign. So the oracle in practice also has to say, here's what I'm going to sign. I'm going to sign the price of oil Friday market close, and I'm going to round it to the nearest cent or whatever. And some kind of standard so that people can reliably anticipate what the messages would be. And then the users can say, well, here's the million different messages this oracle could sign. Let's make a transaction for all of those, right? And the one that they do sign, we're going to learn the private key. So just sort of to contrast, in Lightning, the way we update a channel is we keep sequentially adding a state that spends from a single output. So we have this first state, and we create the second state, and then we invalidate the first state by exchanging private keys. And then we create, now we're confirmed as such on the second state. Then we create the third state, invalidate the second one. So we sort of tear up these old states by revealing private keys to each other. Discrete log contracts looks the same in that, like, you're making transactions. There are two, between counterparties. You're spending from what looks essentially exactly the same as a channel. But you create all the possible outcomes at the outset. So instead of saying, okay, well, at time one, we're doing this, and then as time passes, we create and destroy, we're saying, we initially create everything, and then we're going to destroy the stuff that didn't happen, right? So if we're betting on the weather, okay, here's sunny, here's cloudy, here's rainy, we don't know which is going to happen yet. The oracle will tell us. And what happens is the oracle signs the message cloudy, and that private key then allows this transaction to be consumed by Alice and Bob. So in practice, Alice and Bob could broadcast the wrong thing, right? They have these 3 transactions. And just like in Lightning, you can broadcast the wrong state, right? You can broadcast an old state in Lightning, and then there's a justice transaction, you lose all your money. Similarly, Bob in this case, they sort of neither party lose. But Bob could broadcast the sunny state because he thinks he's going to win and it's going to be sunny. But because the oracle has revealed a private key, and now it's the exact same mechanism as in Lightning, Alice can do a justice transaction, take all Bob's money. So it's the same mechanism, the same equation, so that's pretty cool. We could also make discrete log contracts within Lightning channels. So this would be a nice scalability boost where you can say, okay, I'm creating a output within a channel that's not an HTLC, not a normal thing, but it's its own channel that can have DLCs in it. And if parties cooperate, nothing needs to get broadcast on chain. There are scalability constraints to this. Since we don't have SIG-hash no input or any similar system, you get this sort of n-squared blow-up, where if you have a lot of discrete log contracts or even a lot of channels within a channel, you're going to have to sort of re-sign all of them every time you update any of them. So this is good for like 5, maybe 10, but it doesn't really expand that much unless we had some kind of other SIG-hash. You could also do things like multi-oracle. So you could say, well, I'm trusting this oracle Olivia, I want this other oracle. You can add them up. So you can say, okay, there's 2 public keys from different oracles. We'll just add them the way Schnorr signatures work. If you want to do thresholds, though, it's hard. Another thing that is being worked on, like people are working on, is break apart the message assigned. Because most of the use cases of this are not, is it sunny or rainy? Most of the time, it's some kind of number or some kind of range. We're betting on a price. We're betting on how rainy, how many millimeters of rain fell on a day. And in certain cases, and it makes sense for the oracle to give a lot of precision, but a lot of times the people betting don't want that much precision. So you say, let's sign every digit, right? If we're betting on the price of oil, there's a separate signature for the hundreds place and the tens place and the ones place and the cents and stuff. That way, if people want to bet on just what $10 range something is in, they can have a much more efficient construction. It also allows sort of multi-oracle sanity checks, where you could say, we're going with Oracle A, but we use Oracle B, but only for the most significant figure. So if Oracle B is off 5% from Oracle A, we just go with Oracle A. But if Oracle B is off 70% from Oracle A, then the whole thing times out and we get a refund. So it makes it a lot more flexible. So yeah, discrete log contract use cases. This is initially 2018 at the DCI, presented this, and we made sort of software demo. And now today, there's several companies that are implementing it, making specifications for this. Crypto Garage in Tokyo and SureBits, I think they're based out of San Francisco area, have been implementing this, writing specifications, software for it, and also implementing exchanges. So how do Alice and Bob find each other and talk to oracles? So they're making businesses out of it, which is cool to see. One of the big use cases is sort of stable. I don't know if you call it stable coins, but people want to hold Bitcoin and leverage that Bitcoin, which is the opposite of a stable coin, I guess. And there's also the other side, which is I want to have Bitcoin sort of, or use this sort of cryptocurrency world, but I like dollars, and I like how there's a one-to-one mapping for the numbers I see on my screen and the things in my wallet. And the nice thing is those are 2 sides of a market. Some people want leveraged Bitcoin. Some people want deleveraged Bitcoin. So that's, I guess, the idea of DeFi. So this is kind of a fun DeFi on Bitcoin with no rule set changes. So it doesn't need any new blockchain, doesn't need any new soft forks or any new proofs or anything. So it's usable. It's certainly more limited than something like Ethereum, where you can do lots of contracts. But it does allow a lot of contracts on Bitcoin. Yeah, so that's general idea of discrete log contracts. Verify, don't compute. But it is, I would say, smart contracts. OK, thanks. And I have time for questions. Okay. Couple minutes.
For questions, and I'll start us off. Could you say a little bit more about what SuredBits and Crypto Garage are doing, and what was the path to get to this point of them actually wanting to launch it? Like, what's the?
So we were working on it, like a year and a half ago, and then working on other stuff, and then Digital Garage was interested. They spun out Crypto Garage, which is like sort of the more commercial-facing part of the research they were doing on Bitcoin. They're partnering with a brokerage in Tokyo, Tokyo Tanshi, that is like a fairly large brokerage that wants to do sort of futures and forward contracts settled in Bitcoin. So futures contracts on like interest rates and stuff. So it's an interesting merger of like traditional finance people coming in and saying, oh, cool, this looks like what we're used to, kind of. We want to start doing this. SuredBits is, I guess they're at Boost VC. They're sort of a startup in Bay Area. And they're using Lightning now, but they want to start making discrete log contract stuff as well with the Lightning software that they're developing. And so they're both sort of working on open source protocols for this. So, cool.
Thank you. That was really interesting. Going back to your initial kind of problem description about the reliability of the Oracle and bribes, it seems to me that this construction would primarily have the advantage of making one Oracle decision reusable and therefore removing the economies of the bribery, right?
Yeah.
But so in a sense, so you solve the little case, right? But you may actually create more incentives for government interference as well as bribery, where you have these systemic positions, right? So if you think about something similar to the financial crisis, where certain contracts are triggered if the volatility increases by X, right? And you know that this has an impact on the large number of players, this will actually increase the incentives.
So generally, I totally agree. I probably should have said, like, the examples I sort of jokingly gave, like crashing a car, I don't think discrete log contracts is a good use for that because, well, there's still one car, and so what's the point? Any Oracle reporting on it knows what's going on. Whereas if it's the price of oil, well, it's a huge market. There's millions of people who care about this. And so that sort of disintermediates enough, like they're hands off enough. But yeah, it also has a different problem where if governments say, hey, you need to report that this price is this or something, yeah, then you're not going to solve that. It seems like, but it does seem, I sort of personally would trust the numbers I see on Bloomberg.com or Yahoo Finance more than the numbers I would see in like some Ethereum smart contract thing. It feels like hard. I mean, it's sort of a wishy-washy thing to say, but it feels like, yeah, in the crypto economic idea of like we've got these DeFi smart contracts, we've seen even in the last few months fun sort of flash loan kind of games where you've got you're essentially manipulating Oracle, where it seems harder to try to get Bloomberg to sign off that like the price of gold is 3 cents an ounce. So you're just different trade-offs there. But yeah, definitely.
So kind of dovetailing off that comment, just because the Oracle's blind doesn't mean I can't bribe him, right? And so there's kind of been a failure to launch for oracles. This is an old idea. I worked on this like 5-6 years ago, and like nobody's using them. And more recently, I've discovered in the traditional finance world, a price feed is an oracle, right? And it's also blind. It doesn't know who's making contracts off that price feed. Yet, within the traditional finance system, there's a tremendous amount of work that goes into price feeds. Like, just trusting the number off the Bloomberg terminal, there are probably a team of 25, 50 engineers behind that price feed. And I look at this and I say, you're just averaging some numbers. What's wrong with you people? But there's a tremendous amount of work in going into getting that number right. Maybe that's the reason why oracles have kind of failed to launch. I don't know. Just comment.
I agree,
How
and
are we
I
gonna
think
solve that?
I would say if you can get Bloomberg, if you've got 25 people really making sure that these things, and there's lots of contracts that are based on these price feeds already in the traditional finance system, let's use all that work and just get them to sign a message, and now we can use that. And that, to me, seems like a better thing than starting it. I would trust that more than like a little startup saying, hey, we're making oracles and stuff, because it's easy. You can still bribe them. Where it's harder.
I worked at Bloomberg, tried to get them to do that. I failed.
Okay.
Last question.
Hey. So at Blockstream, we run a price feed, and I can say it is way more engineering work than you would possibly expect. So we might be willing to use discrete log contracts. It's just kind of something we could layer on to an existing price feed, except if you're going to provide a price quote every minute, say, then you need a new public key, or at least a new R value every single minute. And so have you thought at all about how to compress those or pre-transmit them or the story there?
Well, so I'm pretty sure we've talked. Like it doesn't seem possible without pairing, right? So
Yeah.
So yeah, my thinking was like sort of like options contracts. If you have these contracts that have lots of different expiry times, you fragment the market and it's not very liquid. So it seems like options where you'd have sort of Fridays or once a month, and then you wouldn't have actually that many keys. If you did it like every couple minutes, I'm not sure if you even want every couple minutes, but yeah, then it gets also infeasible because of the number of keys involved.
Okay.
So cool.
Thanks.
Okay,
Thank
thanks
you.
a lot.
Thank you, Tadge.